Have you ever just stopped and wondered, are there problems a computer could never solve? I don't mean because it's not powerful enough, but because the question itself is just impossible to answer. Well, today we're diving right into a fascinating battle at the very edge of science, all about the ultimate limits of what we can ever hope to know.
I mean, if you think about it, your gut feeling is probably, yeah, of course, right? We see computers do more incredible things every single day. So surely with enough time and enough power, anything should be solvable. But it turns out that simple question sparks a massive debate between two of the heaviest hitters in science. You see, on one side, you've got the mathematicians. They say, absolutely not. In fact, they proved decades ago that there are hard, uncrossable lines. But then, on the other side, you have physicists. They look at all the weirdness in our universe, black holes, relativity, and they go, hang on a second, maybe there's a cheat code.
So here's how we're going to break this all down. First, we'll look at the actual problem that mathematicians proved is unsolvable. Then we'll get into computing's ultimate speed limit. After that, the really fun part, the wild idea of using physics to literally hack time and space. We'll also cover why physics itself might be the thing that stops us. And finally, we'll unpack what this huge debate really means for all of us. All right, first things first, we have to get our heads around a mathematical truth that's been the bedrock of computer science for almost 100 years now. We're talking about a hard limit that was figured out way, way before computers even looked like they do today. Now, this is a really mind-bending idea. This isn't about just waiting for a faster processor or more RAM. The argument here is that some problems are just logically wired in a way that no computer, no algorithm, no matter how clever, could ever guarantee a solution. Ever. So how do we know this for sure? Well, this isn't just some vague philosophical idea. It's actually a core principle that builds a hard wall that all of computation runs into. Okay, this right here, the Church-Turing Thesis, is basically the foundation of all computer science. Now, a Turing machine isn't a real thing you can buy. It's the theoretical blueprint for any computer. Just picture an infinitely long strip of paper and a little machine that can read, write, and move based on a simple set of rules. The thesis says that if a problem can be computed, this simple machine can do it. So the flip side is huge. If a Turing machine can't solve it, then nothing we'd call a computer can either. So what's one of these impossible problems? The most famous one is called the halting problem. It sounds simple. Can you write a program that can look at any other program and tell you, for sure, if it will eventually stop or just run forever in an infinite loop? Sounds useful, right? But it leads to a paradox. Imagine you feed the program to itself. If your program says it will halt, the paradox means it must run forever. And if it says it will run forever, it must halt. It's a total contradiction, which proves it's mathematically undecidable. That's the hard limit. But this is where the conversation gets really, really interesting. Because physicists, they hear the word never, and they start looking for loopholes in the laws of the universe itself. And this is where we get into ideas that sound like they're straight out of science fiction. This quote really gets to the heart of the physicist's argument. The idea is, yeah, sure, our laptops are stuck playing by Turing's rules. But Einstein's theory of relativity describes a universe where time and space can be bent and warped. And maybe, just maybe, that allows for some pretty bizarre computational shortcuts. And here is one of those theoretical shortcuts, the Zeno machine. Just look at this. It does its first task in 1 second, the next one in half a second, the one after that in a quarter of a second, and so on and so on. By constantly cutting the time in half, it could actually perform an infinite number of steps in a totally finite amount of time. In this case, just 2 seconds. A machine like this could solve the halting problem. It would just run the program for its infinite number of steps and see if it stopped. Wow. Or if you want to get even wilder, how about using a black hole? There's this concept where an observer could hang out in a safe spot while they send a computer on a path that dips in close to the black hole's intense gravity. For the computer, time would slow down so much that it would experience an infinite amount of time to do its calculations. It could solve that unsolvable problem, then just beam the answer back out to the observer, who's only been waiting around for a few hours. I mean, that sounds amazing, right? We could solve anything. But not so fast. Because other parts of physics come along and throw up some pretty massive roadblocks to these ideas. And here is the fundamental clash. That Zeno machine we talked about? It only works if you can divide time into infinitely smaller and smaller pieces. But a lot of theories in quantum gravity suggest that at the tiniest, most fundamental level, what's called the Planck scale, space-time isn't smooth. It's pixelated. It's made of indivisible little chunks.
You literally can't divide time or space forever, which means those infinite steps are physically impossible. But there's an even bigger, maybe more fundamental problem: energy. Landauer's principle is a law of physics that connects information directly to thermodynamics, and what it says is that computation isn't free. Every time you change information, even just flipping a single bit from a 1 to a 0, you have to release a tiny, unavoidable puff of heat. And if you follow that logic out, it's a killer. An infinite computation with an infinite number of steps would generate an infinite amount of heat. It would require infinite energy, and that's a deal breaker. As far as we know, our universe has a finite amount of energy, so it seems like the laws of thermodynamics just slam the door shut on these hypercomputers. So we're left with this incredible standoff. Math says no, some parts of physics say maybe, other parts of physics say absolutely not. Let's just take a step back and think about why this isn't just some abstract argument. The answer actually has huge implications. This whole debate leaves us with two totally different possible realities. I mean, think about it. If hypercomputation is possible, it means the physical universe is fundamentally more powerful than pure logic. The potential for intelligence could be literally limitless. But if it's impossible, it means the universe is basically Turing equivalent. It runs on the same fundamental rules as your laptop. And that would suggest there's a hard ceiling on knowledge and that some truths in the universe might be forever out of our reach. Ultimately, this whole thing boils down to one massive question about the very nature of reality. Are the ultimate rules that govern everything the clean, abstract, and limited laws of mathematics? Or are they the messy, powerful, and potentially limitless laws of physics? Right now, that's a question we just don't have the answer to.